Hey guys, thank you for coming. So today we'll be looking at this particular theorem. It's despite the fact its name, it's actually first proven by Euler. Very classic. So it says let E be an prime. Then there exists A, B, and Z or P whatever such that P is equal to A squared plus B squared if and only if P is congruent to 1 mod 4. So there's a couple of reasons why I really like this theorem. First of all, I think it's really nice. You sort of connect two really different sort of concepts like mod 4 and like a prime number that looks like this that don't seem to have much connection. I think that's quite nice. The other reason is actually because like I said, despite the name, the first proof came from Euler, and I'll show you guys the first proof. Actually, it's really like long and really disgusting. So yeah, we won't be looking at this today, but as you guys can see, there's very little machinery going on as far as I can see. It's just algebraic manipulations and like observing stuff, which isn't really nice, which is contrasted to today's sort of proof. So so the proof we're going to present today, it's literally like it uses just about everything that I've learned from 320, which I thought was really nice, and it really shows how like powerful the tools we have are right now. Because yeah, so right, so the main sort of thing we're going to be developing is known as like the ring Zi. So I'm going to assume everyone is like familiar with like the concept of like PID and stuff. So we'll take a definition first. Definition. So let R be an integral domain. Um, then R is a Euclidean domain. If there exists some lambda from R without 0 to the set to the set Z greater than or equal to 0, i.e. the non-negative integers, such that for all I use x, but I'll use AB member of R with B not equal to 0. There exists QR such that x is equal to yq plus a is equal to bq plus r, and the lambda of r is strictly less than the lambda of b. So this you guys can see this should be quite familiar. So for example, so a couple of examples is simply going to be like e.g. z, where we take lambda to be like lambda of like n to be equal to the absolute value of n. So that's one of them. Second one is um, k of x, the polynomials over some x, where we take like lambda of p to be equal to the degree of p. And well, I'm assuming everyone's done like the Euclidean algorithm, so that's where the name comes from. It's simply a domain in which you can do the Euclidean algorithm. So what's particularly interesting about this thing is this proposition I'm going to use now. So proposition, so the Euclidean domain, then R is a principal ideal domain. So like for those who might have forgotten, a principal ideal domain is simply an integral domain where every ideal can be generated by a single element. So the proof is quite short actually. So suppose I is an ideal, then select so if I is equal to the 0 ideal, then we are done because like it's generated by 0. Otherwise, we pick some x that's non-zero, and then such that this thing is minimal. So this is like for example, in like the integers, we pick some natural number that's the smallest and an ideal. Then we take now take any y member of I. So we're going to show that this is member of the ideal generated by X. So so then there exists QR member of R such that y is equal to xq plus r. So we have the assumption that so if r is non-zero, then we have the assumption that lambda of r is strictly less than lambda of x, which like this contradicts is minimal. Sorry, that contradicts this thing here. So that means therefore we must have r is equal to 0, equal to not equal to is equal to 0, and then we're done because we've shown that that y is a member of this thing, and obviously this thing is a subset of I because by assumption, right? So yeah, that's nice. So in particular, what is particularly interesting here is that like a PID is a UFD. I'm not gonna bother like proving that here. It's proven in Ireland and Rosens and the references, but so what that means is UI is a UFD, and therefore it has prime factorizations. So you might like the most natural question to ask is, oh sorry, no, I haven't proven that it's a PID. It's a Euclidean domain yet. So that's our theorem. It's that I is a Euclidean domain and domain. So in particular, a UFD PID is a Euclidean domain is a PID, which is a UFD. So the proof is it's simply okay. We define lambda of so of a plus bi is defined to be a squared plus b squared, which is equal to the absolute value when we embed zi in the complex plane. So and then so how we prove that this thing works is suppose we have some y is equal to y1 plus and x is equal to x1 plus x2i. So let z, which is equal to z1 plus z2 be defined as like x over y when we embed it inside the complex plane. So so if this thing is inside the what do you call the zi, then we're done because like our r is simply 0. But otherwise we pick pick our q1 q2 to be such that q1 minus z1 is less than a half, q2 minus z2 is also less than a half. So like why can we do this? Well, it's just it's just easy to see if I draw a picture actually. So if my my qi is here, then it's between some like n and like n plus 1 and oh, I should say member z, and I can pick whichever one it's closer to. So that's how I get my z, q1, and q2 is done in a similar way. So then it's just a matter of like basic algebraic manipulation to see that so that you can show that x over y minus q is less than or equal to a half, because that's pretty much like you square this, you square this thing and you square this thing at the end together to get a half, and that's how you get this thing. And then multiplying, then we finally get lambda of x minus qy is equal to y of x minus y minus q, which is equal to less than or equal to a half times y, which is equal to a half times lambda of y, which is obviously strictly less than lambda of y, in which case we're down to. So that shows that zi is a UFD. So yeah, questions? Can someone say something, because I kind of feel like I'm tweeting myself. Okay. Right. So okay. So now the natural question to ask is what do the primes of zi look like? So I'm going to partially answer that question right now with like this proposition. Let p be a number. Then either then if is not a, I'm going to call it a Gaussian prime, which is a prime in the ring Zi, which is the ring of called the ring of Gaussian integers. So then p is pi times pi conjugate, where pi is a Gaussian. Cool. So yeah, the proof is quite nice. It's I found it in Arten. It's simply says, okay, so suppose E is not a Gaussian prime. Okay, so then since okay, you can show quite easily that the units of zi are simply plus or minus 1 and plus or minus I. That's simply a result of the fact that when you multiply two Gaussian integers together, their modulus, their absolute value must increase. So if it divides 1, it must have modulus 1, and obviously those are the only 4. So now suppose it's not a Gaussian prime, then it has a proper divisor I, which is a member of, which is not a normal integer, because that would contradict the primality of p. So then now we also know, we know that this divides this, therefore pi divides p conjugate, which is equal to p. So therefore pi conjugate also divides p. So therefore pi times pi conjugate divides p squared. And so that means and also we observe that pi times pi conjugate is a member of is a member of z, because it's two conjugate complexes just multiplied together. So that means this is a proper divisor of p, because pi is a proper divisor of p. Therefore, we must have pi times pi conjugate and yeah, QED. Sweet. So right. So okay. So one thing we do observe is that so if pi conjugate and pi, where pi is equal to a plus bi, then p is so already we're seeing some sort of resemblance between this thing and like so okay, now we're now gonna go on to the main part of proof now. So okay, so it's just okay, consequence of a couple of limits. So lemma number, then the following so I'm just gonna clarify, when I say prime number, I mean like a yeah, if I say Gaussian prime, that's it could be a normal prime as well, but it is obviously a Gaussian prime.
Oliver, I think you're breaking up there. There's some background and you're kind of fading into the background for some reason.
Uh, on my screen.
Your voice. Is anyone
Oh,
having those not hearing Oliver well at the moment, or just me?
It's just electric static.
oh really? Oh, sorry. Yeah, I'm not too sure. Can you guys hear me now?
Are you plugged in, or
I'm not
maybe try
using.
unplugging?
I guess it's continuing. Can you guys hear me? Okay, okay. Can, okay, yeah, I'll just continue. Yeah, see if I hear this. No. So yeah, in the following segment, the one I
Yeah, I can't really hear you there, Oliver. Sorry.
um, are you connect?
It's really weird. I don't know what's going on.
I can't hear you then. Maybe try reconnecting. Just kick him on.
Yeah, I don't know what that was.
Modern technique.
Does he need the link? Let's invite. Doesn't everyone love technology?
Literally the best.
Welcome back, Oliver.
Hey, can you hear me now?
Yep, crystal
Alright,
clear.
so, okay, cool. I don't know what happened there. Can you let me share my screen?
What was that?
I says here you disabled the screen sharing.
Oh, I have to make you a host. Try now.
Let's try it. Right, sweet. Right. Yeah. Okay. Where do I sort of lose you guys?
When you wrote TFAE.
Oh, okay. Yeah. Okay. So
Not
then the following are equivalent. So it's a P is a Gaussian prime. Then this thing here is a field, and this is irreducible in if the finite field of f of p of x. Yeah. So yeah, the proof is this is where I really like this because it just uses like 320 machinery in a pretty nice way. So equivalence of 1 and 2 is simply because I say this trivial in notes, but I'll just briefly explain. It's if P is a Gaussian prime, then P is maximal. Then then this thing here is a field. The converse literally uses the same thing, because if it's a field, then if this thing is a field, then this thing must be a maximum ideal. So the nice thing here is 3 and 2 are equivalent. So how that works is it's simply like there's a like it might be really obvious, but these two things are literally the same thing. So like what I meant is, for example, z x portion out by p is isomorphic to f of x. Why is that? So basically, it's just like I define the isomorphism as like I define this to px in the natural way. So basically like a0 plus blah 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 plus a n x n, that maps to like a0 the residue, then a n x n, and obviously the kernel, so this thing is phi, so obviously these two are isomorphic, and therefore if I quotient out by so to get this, I simply quotient out this thing by x squared plus 1, and therefore the
Oh, Oliver, interjection again. You're still getting a lot of static there.
oh,
Is your pen? How does your pen work? Just out of interest.
I have no idea.
Wait, try holding your pen up in the air without touching the tablet and say count to 5 or something.
Can you hear me now?
No.
Uh,
So you're using your mic on your Surface, right?
yeah.
Right. I have no idea how to fix this. Do you have a headset or like headphones with a mic on it, or just a standalone mic?
I do actually. Just okay. Sorry, give me a sec.
No worries, thanks.
It's weird though, because I've been using the Surface to record lectures and writing it in no problem. So it can't be about
Yeah, I don't know. Maybe it's something like, well, it's some sort of interference. So maybe the mic, something magnetic is next to the mic or something. I don't know.
Yeah, it must be.
Well,
Can you hear me now?
yep.
Like clearly or not clearly?
More clearly, but there's still background.
Okay.
Wait, let
Yeah, my
me.
iPhone started doing some really fun stuff recently. I don't know if it's related. Like the screen just somehow like flashes sometimes.
Okay. Yeah, it's gotten worse again for some reason.
Okay. Can you hear me now?
Oh, yep, that's
Oh,
good.
okay, cool. I just turned on my speakers. For some reason the audio on these on this on my head on my earphones don't are always on the maximum. I can't turn it off for some reason. So yeah. Okay, let's go back. Okay, really sorry about that. Just stop me again if like anything bad happens.
Will do. Yep. Sounding
Cool.
really good now.
Sweet. Okay, now continue. So yeah, we defined now. So basically, yeah, this thing and this thing are isomorphic. Therefore, this thing quotient now by this thing is simply this thing. Therefore, they're yeah. So right. So our next lemma is so next lemma is so let P be an odd prime. Then there exists some uh, integer x satisfying such that x squared is congruent to -1 mod p, if and only if p is equal to is congruent to 1 mod 4. So already we're seeing more resemblance with the original theorem. So the proof is really nice in my opinion. It's just a culmination of everything that's taught in 320. So okay, so okay, we consider this group the multiplicative group of this thing. So it's so obviously -2 the -1, the order of -1 is equal to 2, and it's the -1 is the only element such that that has order 2. So now therefore if x squared is congruent to -1 mod p, then x would have to be have to have order 4 then we have order 4. So there's that. Now the other direction, conversely, suppose x equals 4, then okay, x squared, the order of x squared would have to be 2. Therefore x squared is equal to -1 because yeah, because -1 is the only element of order 2. Cool. So yeah, that's yeah, that's the theorem. That's the of course. Yep. Sorry. So wait, what's it going to this? Then this is equal to 4. Okay, and okay, so yeah, so since if P is cyclic, because that's proven. If you don't know the proof, you can look it up and see it. It's really, really nice. Therefore, there exists x a with a hat such that is equal to 4 if and only if 4 divides the order of this group, and that's equivalent to the since okay. Since the order of this group is p minus 1, this is equivalent to p being 1 mod 4, right? Yeah, so that's the two lemmas, and now finally we have enough theory to cover the theorem. So I call it a corollary actually. Corollary. So let p be an odd prime. Then p is equal to a squared plus b squared for some a squared plus b squared if and only if p is congruent to 1 mod 4. So that puts everything we've done so far together. So okay, so by some proposition above, p is a squared plus b squared if and only if and only if P is not a Gaussian prime. So by this lemma up here, that means this means x squared minus 1 is not irreducible, i.e. it is reducible over the finite field of order P. Which is equivalent to and equivalently. So since this is a polynomial of degree 2, if it's reducible, it must have a linear polynomial, i.e. a root, which means there exists some A with a hat member of this field such that A squared equals minus 1 is equal to 0 inside the group. So that's equivalent to there exists some A member of Z such that A is congruent to -1 mod P. And okay, so that is equivalent to P is congruent to 1 mod 4. And that is the proof. That went a lot quicker than I thought it would actually. Cool. So so I wanted to sort of fit in with Tristan's elliptic curve talk a little bit, but unfortunately I ran out of time to sort of go through the details. But if you notice the quote at the top of the notes, it's given by Andrew Wiles in a lecture. I just realized it was a little bit misleading to put it at the top because he wasn't referring to the statement of Fermat's sum of squares theorem. He was actually referring to this theorem. So to these two theorems. So theorem. So the only integral points on I'm going to call it the variety defined by y squared minus x cubed plus 2, which is equal to the 0 set. It's like yx given y squared minus x cubed plus 2 is equal to 0 are 3 and plus and minus 5. And theorem, the only integral points on this elliptic curve, y squared minus x cubed plus 4 are 2 plus or minus 2 and 5 plus or minus 11. So the details are in the link which I've given, and there's more discussion on these type of equations. They're called Mordell equations. And that's it for me.